Hello everyone. So welcome to the next lecture, and now let us look at the next source of renewable energy generation. So what we looked in last couple of lectures was solar, and as you can imagine, since solar is being termed as the highest contribution to the renewable energy generation going forward, so we spent quite a bit of time on that. So next big source that we will spend time on is wind energy. And as you know that when I showed you the energy transition data, or the future pathways, many of you would recall that it is basically the combination of solar plus wind, maybe some bit of bioenergy, and hydrogen, which was termed as the whole transition pathway was depending upon these four things primarily. So wind plays a very significant role in this whole transition story for the power sector, and overall from the generation side, like when we say that whole of this energy transition would depend upon electrification, and in under electrification also the sources should be such that they should be carbon friendly. And many of you will remember the graph which I showed you earlier, where wind was shown to be one of the most carbon friendly technology after nuclear almost. So nuclear had its own concern, which we'll cover later on, but overall that's kind of significance wind has. So wind has double significance: one of the highest source in the world along with solar. And in fact, wind was the earlier starter, and I'll show you like what wind has achieved so far. And also along with that, one of the best carbon footprint in terms of all renewable technology or overall energy generation technology itself. Now, so let us first start looking into some numbers. So wind has become one of the main pillars of global decarbonization strategy. The reasons are pretty simple, because the large scale low carbon electricity generation is possible through this. Rapid deployment is possible because it has got a lot of policy support historically, and also continue to get some policy support. There were some glitches in between, but now I think wind has got a renewed life recently, and I'll show you why. Many of you would also remember the levelized cost of energy graph, and as you could see that the declining cost of electricity due to technology, learning and scale, and wind has been one of the cheapest costs in terms of, at least the onshore wind has one of the cheapest LCOE amongst all the renewable energy sources, in fact amongst all energy sources right now in the world. And one thing which is very interesting for the wind, and which we'll spend some time on, is that wind has a very good complementary generation potential with respect to solar. So it's a very interesting technology from that perspective, that it's not only clean, it's not only renewable, it's not only being deployed at a very large scale. This complements the next biggest source of energy which is being talked at the worldwide level for energy generation from renewable energy sources, namely the solar technology. It kind of complements the two generations. So while CUF individually can be a concern for both of them individually, but when you put them together, the CUF actually becomes pretty high, and that is a very interesting potential which wind energy gives you. So that's why wind becomes a very important factor. And overall what we have seen is that wind actually was a much earlier started, while you saw that solar kind of started its journey in 2010. Wind started its journey in late 1990s, and it has been in deployment phase since 1990s itself. A lot of European countries had a head start to start deploying many of these windmills much earlier. Before than that also, like Netherlands is one example which has a much longer history for wind energy generation. But apart from that, a lot of European countries started this wind energy generation back in 1990s itself, and it has taken a shape where it is more than 1 terawatt of net deployment. And since its CUF is higher, so from a generation perspective, it is already a significant generation worldwide if we compare it to solar also. So that's pretty interesting. And also the growth year on year has been a tune of almost 100 gigawatt on a yearly basis. Slower than solar, agreed, but nonetheless very significant number if we start looking in this number in isolation. What wind has done, as I said, that what wind has done over last many years is that wind has contributed very significantly in several countries already. For example, in Denmark, more than 50% of the net electricity, more than 50% actually comes from wind as we speak. And this is a very significant thing, that a country which depends very significantly on renewable energy, and that too wind. So almost, if I am right, almost 60 to 70% of net Denmark electricity gets generated through the wind energy source, which is a very significant number for any country to have. In fact, countries like Ireland, Portugal, other countries also are about 30%. Germany, United Kingdom more than 20%. So as you can see, a very significant portion of the net electricity consumed in these countries is coming from these sources. Globally, wind contributes almost 8 to 10% of electricity generation and about 4% of total energy generation, if my numbers are right. But numbers are not that important. What is more important is to understand that this is one of the very significant portion of this whole of this renewable energy transition which is happening. We all know that what leads to wind generation. So it's basically uneven heating on Earth's surface by solar radiation, which leads to the differential temperature at two places, which leads to a differential atmospheric pressure, and because of the rotation of the Earth, all these features put together, and plus on top of it we have areas like mountains and oceans which has a different temperature compared to the land temperature again. So all these things put together leads to zones which are sitting at different pressure and different temperature, and for that equivalence to be maintained at a pressure level or at a temperature level, for this to maintain this equivalence, there is a gradient of molecule movement from one side to the other side, and which leads to the wind generation. And as you can imagine, the higher is the temperature difference between the two specific areas, and if those areas can be in contact with each other, higher will be the wind velocity between those two places. So this is a resource which will continue to be there, and like solar radiation is present, since solar radiation is present, so wind also will be present almost all the time. So that's a it's a as renewable as solar is, and so it's almost like a universal source, and it will not get depleted. Only thing is that at what cost can be extracted, and what could be the efficiency of this extraction, what will be the net policy level thing, and what are the technology level challenges in overall extraction is what will the major cause of concern. Otherwise, in terms of the resource availability, this resource will be available for forever almost. That's how we can put it. And then if we start looking into numbers more and more, what we see is that with this kind of a global kind of a distribution, the availability of wind is slightly different from what was the availability of solar. If you all remember, solar was available around the central line of the Earth. So that solar was available. Solar was almost available around this line, on both sides of this line, and plus barring Australia in addition to that. But wind, as you can see, wind is more available towards the northern side or towards the southern side, not so much in between. The wind is not so much available. Nonetheless, it is available, and that's why, since you can see that a lot of wind availability is there in the western world, European world, America, Canada, Russia, and Australia, those part of geographies has, and specifically if you look at down towards like areas like Brazil and stuff like that. So you have a lot of ability of wind in those specific geographies. So with that, the wind has actually taken very large portion of the energy generations in those specific geographies because of this availability of the wind resources. And also, it is not only because of the, it is not fixed in those geographies also that where the wind will be available. As you can imagine, since it's a temperature difference thing which is responsible for it, and it is the sea and the mountains which will lead to the differential temperature more and more. So from there you can easily extrapolate that this will be available, high potential of wind will be available in coastal zones, very open plains, offshore regions, mountain passes. So there will be specific locations within those specific geographies also where the wind potential is high. Within that also there will be specific locations wind will be available more compared to other places. So that's why, unlike solar, where you can basically do a broader area radiation identification and you can do a broader level of deployment of resources, wind becomes slightly more tricky in terms of assessment. Wind becomes slightly more tricky in terms of potential, in terms of its availability. So that's why wind is slightly more tricky in terms of the exact assessment, in terms of how much resource is available and how it can be deployed and what can be done with this source overall, right. Then once wind is available, how do you convert this into electricity is very simple. Basically wind is blowing, so that's kind of a kinetic energy. That kinetic energy rotates the blades, and so that gets converted to mechanical energy. And from that rotational blade, basically you put that rotational blade on a generator, and through that generator basically converts the mechanical energy into electrical energy. That's a kind of a chronology in which wind kind of works. So basically wind blows through turbine blades, create aerodynamic forces. These forces rotate the rotor connected to the shaft, and once the shaft starts to rotate, generator located in the knuckle starts, it drives that generator which is available in knuckle, and through that mechanical energy is converted into electrical energy. So then that electrical energy, once it is generated, that electrical energy then can be put into grid, and that can be transmitted to for consumption. So that's how it's a very simple phenomenon, not a very complicated phenomena to have. It's almost like a simple plug and play kind of a model. Once you have the right turbine, once you have the right generator, once you have the right blade which is available, and so that way the electricity can be generated. As you can then start to see that what it will depend upon, it will depend upon wind speed, it will depend upon the type of blades, it will depend upon the type of generator, it will start depending upon many of these parameters. So let us look at some of these limitations, and why we need to look into those limitations is not only from the technical side, but those limitations also lead us to a situation that where the windmill can be deployed. So I told you the situation that windmill cannot be deployed everywhere. Windmill need to be deployed with some specific studies to be done around the over general availability also. So what are those typical parameters that how it can be designed? What are some of the minor nuances that you need to worry about in terms of overall wind farms which are put together, because that kind of drives the policy or the financial model of the wind energy conversion overall. Right. So in terms of power available from the wind, power depends upon the speed of the wind which is available, so there is a cut-in speed. Below that cut-in speed, the wind doesn't have enough kinetic energy available in itself to turn the blades. So if the blades cannot be turned, the power generation will not be there. So once you start to cut in, so that is typically about 4 meters per second kind of a speed above which it starts generating. Then there is a cutoff speed up to which it can generate the energy, and so there is a rated speed up to at which it gets a maximum efficiency in terms of power output from the windmill. And beyond that it starts to reduce its generation, and beyond a point you will have a cutoff speed above which you cannot generate, because then there will be a high chances of the wind damaging the windmill itself. So that's why there is always a cutoff speed which is put in most of the windmills. So as you can see that the generation of the power is directly proportional almost to the cube of the wind speed. And since it's proportional to the cube of wind speed, that's why the location of windmills becomes of prime importance. So a same windmill put in an area where the wind is available around this speed versus this speed can lead to a huge difference between the generation from the same windmill which is possible. So this kind of variation is not there in the solar cells. So that's why solar cells are slightly more forgiving in terms of some errors for deployment, while windmill will have a much more stringent kind of a deployment norms if you look at overall, because it depends upon the cube of the speed of the wind, it depends upon the air density, it depends upon the rotor swept area, power coefficient. So higher is the air density, it will have more mechanical energy associated with it. So at the same speed it can rotate the blades faster. So it's all about the kinetic energy which is present in the wind itself, which will lead to this energy generation. And with this situation, as you can see, it becomes highly critical where these windmills can be deployed. So that is one nuance that people, policymakers or the deployer needs to keep in mind. Second is that whenever the energy is generated, also not all energy can be extracted. So if a turbine can extract all kinetic energy, the air behind a rotor would stop moving. As you can imagine, just to put a simple kinetic energy balancing equation, and you can find it this easily. I am not going to those technical details as part of this course. So additional wind could not flow through the turbine at that case. So aerodynamic theory shows that maximum limit through which the efficiency can be achieved is about 59.3%. So typical windmill kind of achieves about 40 to 50% efficiency related to the available wind energy. So it is not that when you talked about that maximum energy can be available here, what can be extracted from that is typically about 40 to 50% is typically what can be achieved. 50% is the ideal limit. So when you do the calculation, it is not only about the wind speed that you need to worry about. What you also need to see that what's the extractable beds limit that you can potentially extract from these windmills. Another thing which is of concern, as you can see that from the earlier equation of the power generation. So while we talked about the wind speed, another thing which was important you would have noticed was the swept area, that what is the area which the sweep of the wings of the wind is kind of covering, because that's where it will be cutting the wind. And so how large is the swept area, that will kind of directly determine that what's the power that a single location windmill can also generate. So a lot of research has happened on this, and research continues to happen. So if you start looking into history, when these windmill kind of came into picture, it was being talked about windmills for less than 100 feet high. These days current windmills which are running is about 300 feet of height. So Onshore windmills are usually about 300 feet or 120 meters high is typically what is being deployed these days. For the offshore wind, I'll be talking more about what our offshore winds are. Offshore winds started around this 328 feet or again 120 meter to 150 meters is typical deployment which kind of started on these offshore winds to begin with. But what is happening right now is that the research which is running around, as you can imagine, that we are talking about one deployment, and then through that one deployment we want to maximize the generation. If you want to maximize the generation from a same horizontal location, so see this is all vertical erection, horizontally the area is almost similar. So since land will become a cause of concern, you want maximize the generation from a single point of deployment. So for you to do that, the windmills are getting higher and higher, and the wings are getting longer and longer because to increase the swept area. And of course, this makes the whole installation part of the windmills very, very tricky, because as you can imagine that these are sometimes put in very, very remote area. Just the transportation of these big windmills from the point of manufacturing of these windmills to the point of deployment becomes very tricky. So I'll encourage some of you to look at some of these videos online on how these big windmills are transported from the point of manufacturing to point of deployment. That is a very tricky thing that this industry is facing. But just to put in perspective, this 328 feet is very high. So who might have seen the Statue of Liberty? So Statue of Liberty is about 305 feet high. So these are very, very tall windmills that we are talking about out here. So it's not a small installation that we see. The modern windmills are using large and large rotors and are now exceeding about 150 meter, and we'll see that what is the implication of these things in terms of energy generation and possibilities around that. Another technology which is getting developed a lot these days is vertical axis wind turbine. It's not that it's new, it has been pretty well known historically also. So as we have been so far talking about the horizontal axis wind turbine, where wind kind of rotates and the deployment is in the horizontal direction, the movement of the wind is in the horizontal direction, and the wings are moving in that plane itself. So that's one kind of generation that we are talking about. The other kind of generation which is there is about the vertical axis wind turbine, where you have a kind of an axis which kind of vibrates around a single position, or so depending upon the wind speed. So it has advantages that it can work at very, very low wind speed. That's one advantage. The disadvantage of this is that the efficiency of such systems is usually poor, because the rotor axis is perpendicular to the wind direction. It is usually have much lower efficiency. It is limited large scale deployment is a concern on these things, while horizontal axis wind turbines, which has been historically being used for a lot, rotation axis is parallel to the wind direction, and it has much higher efficiency because of that. And so overall this technology has been historically there and historically has shown very good results. But vertical axis wind turbine is a big area of research these days, specifically for geographies or for places where high wind speeds are not possible or available. It is being taught a lot in those specific areas. Even some research labs in US also trying to show that even for some of the offshore wind deployment or projects also, maybe wind axis, vertical axis wind turbine may be an interesting solution. So more research is going on in that area. So let us see that how does it progress, but that is another technology which you should kind of keep an eye on. Some of the research which are also going in this area is about maybe generating the wind power even on highways. Some of these winds are not very reliable, like from a movement of a car, since it cuts through the wind and there is a movement of the molecules at that point. So a bit of wind generation or bit of kind of a aerodynamic pattern generation takes place around that time, and so that can lead to some kind of a vibration, and which people are trying to capture by putting some small vertical axis wind turbines on highways also. So a lot of research is going around this area, but this is a new technology. Like it's not new, but it's kind of a new kind of a research is going around on this a lot these days, right? So while we say all this, what we need to now understand is that what it entails, what is the limitation factor of some of these wind turbines, what is happening at a worldwide from an economic level perspective and stuff like that. So just for that, let us try to understand that what goes in a windmill. So how does simply it works is that there is a rotor blade that captures the wind. There is a rotor blade which kind of captures the wind, and then hub connecting to the blade kind of moves, and knuckle is what contains the gearbox and the generator, and there is a tower which is supporting the whole turbine structure, because it has to support this big weight of the knuckle and the wings and overall. So it's kind of a pole on which a huge weight is being put, and that weight is not stationary, because as soon as the wings on these things move, So that kind of puts additional pressure on this structure. So as you can imagine, that a lot of metal kind of goes into this thing, construction of this thing, because it needs to be a very sturdy structure which needs to handle all this kinetic energy of the wind which it is facing. It has to handle the kind of moment of the wings which it will go, the blades it will go through, and on top of it, so it can really sit in windy areas. We want to really sit in the windy areas. Now when it is sitting in a windy area, it needs to have that kind of a sway or that kind of a possibility that wind should not be able to damage some of these windmills, and that is another concern, because of which some of these structures are very heavy structures which are put through. Another thing which I have not shown here is that there is also a thing that is a kind of a tilting possibility. Like sometimes these blades are kind of having a lot of force issue, so or having an issue with where they are not able to maximize their power generation. So they have the possibility of slight bit of tilting by some kind of a moment with respect to its horizontal axis also. So that's another possibility which is there in these windmills, and that structure needs to support that kind of a thing also. But that is done for two purposes, like just to avoid that the windmills should have the resistance on the wind, and that if resistance is very high, that it can lead to the failure of these windmills also at times. So with all this, what is being done is that a lot of big wind farms are being deployed. So it is typically deployed in big areas, because once you identify a potential area where this kind of power generation can happen, you kind of want to do a large scale deployment. And because then what you want to really do is that you want to exploit the potential of that area as much as possible, and then you can then put it together on a grid as a single generation point to kind of have a to avoid the grid should be put on each different structure if it is not done this way. So overall, what is being done, like in case of solar, wind farms are also kind of increasing more and more large in size. And also what is happening is, since the land area can be limited, and since the sea itself can be a huge potential area, so area which is joining the sea and the land, that can be a very interesting area to have, because the wind speed sometime in those areas can be very high. So what is getting developed these days also is what is called as offshore windmills, where so onshore windmills is what I have talked to you about, these are very popular, and they are running about 120 meters these days, and they are projected to move towards 130 meters. Offshore windmills are already working at a much higher capacity for the same height itself. Like just to compare, for the hub height of 130 meter, which is projected to be in 2035, a typical capacity of a windmill will be 5.5 megawatt, but a typical offshore windmill would be of about 100 meter itself can have a capacity of 6 megawatt, just because we've got two factors: the wind speed can be higher, and also the wind availability in the day also can be higher. So it is about two things. Again, remember what I talked in terms of solar also, like CUF. So CUF of offshore windmills are higher, and also the specific wind which is available is also higher. So overall, lot of installations slowly these days are also talking about offshore wind turbine deployment. So in terms of, if you just kind of compare at a very high level, onshore winds have a lower cost of installation and lower maintenance cost, because they are sitting on a land area. So of course reaching them is easier, and maintaining them is easier. They can be easily connected to grid. And that's why they kindly constitute, or most of the wind power which is generated today is because of the onshore wind. Offshore has a huge potential, because stronger and more consistent wind speeds are available for this area. Larger turbine and higher capacity factors are possible into this thing, but at the same time it would also mean higher capital and maintenance costs. So this will have its nuances. So what will finally determine is that what is the potential of a specific area, and what is the cost of generation, and there we will see some more numbers on what it looks like. When we are doing this wind farm deployment, one factor that we need to kind of worry about is what is called a wake effect, where when the wind is cut by a specific windmill, it can have an impact on the wind availability for the next windmill which is just behind it. So that's why the part of the energy, since it is extracted, some wind speeds can be decreased and some turbulence might increase. So that's why there is a wake area which is kind of created between this windmill and the next windmill. So when the deployment kind of happens, so usually there is a minimum distance which is kind of kept between the two poles of wind generation, and sometimes it is also not in the same direction. Sometimes there is a cross kind of a deployment between one tower and the other tower, just to avoid that kind of wake effect impacting the other thing. So a lot of technicalities has to go into all of this deployment, right. So for finding out the potential of these windmills, what is usually done is that we do a wind resource assessment. That is usually done using a wind speed at different heights. We kind of go about finding out that what is the wind speed which is available, what is the long term wind pattern for that area. Then we find out what is the estimate the overall energy potential of that specific area. We evaluate the whole terrain, we do the surface roughness measurement. So overall, a lot of kind of background work is done before we kind of do this windmill deployment. As you can imagine, that it depends a lot on the wind speed, it depends upon a lot on the availability of wind throughout the year, and what kind of seasonal variations are we talking about. So a lot of technicalities has to go around, and this all has policy implication, because then when we are releasing tenders, these tenders are has to be with much more rigor, that the assessment of the resource has to be done, otherwise the whole tender specifications can be not met, right. The advantage of this whole thing, once you do all of this exercise, and since wind is a very interesting available resource throughout the year, one of the big things that the wind is kind of seeing all over the world is that while typical solar PV capacity utilization factor was in the tune of 18 to 25%, India was sitting about some 19.5 to 20% of CUF. These onshore wind can have much higher potential of 30 to 40% in terms of CUF, and that is impressive. So same 5 megawatt of installation in that term can give about 20 to 30% production, which could be higher, which is what it leads to the lower LCOE of windmills more or less all over the world. Offshore winds, as I showed you, that CUF can be higher because of wind speed. The availability of wind throughout the day could be higher because of the temperature difference between the sea and the land area. And since these installations are usually around the coastal area itself, few hundreds of meters of around that within the coastal area itself, so wind speeds are usually very high. And with this in mind, the offshore wind can have capacity utilization factor which is much higher than that also. So that's a very interesting phenomenon to understand. So with all this put together, we can do a energy yield estimation of the wind, that depending upon the wind speed availability, depending upon the what kind of wind distribution available, what kind of turbine is available, what kind of wake losses we are doing in our deployment, we can really do a kind of a estimation in terms of what exactly a power will kind of generate. And of course, there will be a upper cut limit above which the power will not go up, and then at around 25 meters per second, some of you would imagine that this was a kind of cutout speed above which you don't allow the windmills to kind of operate, and then you kind of lock the wing, you don't allow the wings to move, otherwise there are chances of the wings getting damaged. With all this put together, what is happening is that the global capacity, as I showed you this data earlier also, the capacity has really grown pretty big. We are talking about more than 1 terawatt. I will talk this number with you. Annual capacity is exceeding about 100 gigawatt year on year, while historically it is Europe and Brazil and United States which has kind of done more deployment. More and more deployment is happening in countries like China, India. So India is also kind of catching up this race, and it is becoming one of the top generators of this renewable energy sources from wind. So if you just start looking at this graph, so India is coming out almost at the 4th or 5th place in the world, which is very significant given the late start which India did, as kind of a serious dent on this line. So, but this is becoming interesting, and from that perspective. And of course, what led to this, and we have already talked about this number a bit, but cost trend in wind energy has been pretty impressive. This is one of the best LCOE which has kind of shown all throughout its journey for last many years now. So if you start looking at it, while solar kind of started giving this LCOE here itself, wind has been giving very impressive LCOE for almost since 2010, 11 or maybe around 14. It has been given very impressive LCOE. Of late, it has kind of increased a bit. And the reason for the increase of this is that some metal costs have kind of gone up, and some supply chain issues have led to this increase in this cost of onshore wind and deployment. But still, it is one among the lowest cost sources of electricity still as we speak as of now also, just comparing to solar. So now it has kind of caught with solar. So solar, and now this is kind of equivalent. It used to be, at this point it used to be kind of lower than solar, but it is now almost equivalent to solar if we talk in terms of actual LCOE. Offshore wind cost, however, is slightly higher. So while onshore wind was about $50 on an average basis, offshore wind has been on the higher side, and the overall total cost of installation also has been high. But what is seen is that, and the reason for that is that there has to be on the sea construction and installation, offshore transmission structure has to be put, and maintenance has to be done in the very harsh marine environment. So that's why the offshore wind initial cost of capital has been pretty high earlier. What we have seen is that with the technology improving, that cost trend is kind of coming down, and given the impressive cost of COF, since the COF is pretty high, the LCOE has started to look very impressive for this specific technology, and now this LCOE is kind of catching up with the onshore wind also. Like if you look at onshore wind, the average is about at $50 per megawatt hour, and this is kind of reaching about $76 per megawatt hour. So this is kind of approaching that number slowly, and then what is expected is in the next few years the offshore windmills can start looking more and more impressive as the technology kind of improves, as more and more economies of scale kind of sets up into this domain, and so this kind of becomes a interesting proposition. Now, so as many of you will recall that just a few slides back I talked to you about this heavy structure which we need to put for these windmills to kind of come through. So, since that is the case, so if you start looking at the material uses of this wind turbine, no surprise that the highest amount of material which these windmills uses is steel and iron, because a very heavy steel and iron kind of a pillar and which needs to be erected, and it needs to be in place for these windmills to be holded at a place. And second one is the highest is the composite material, which is primarily the blade material. So these two are the highest kind of requirement as far as these windmills goes. And then there are copper requirement, then there are some rare earth metals which are required as part of the motor, as part of the whole energy generation process, and some of these materials will start becoming tricky as we kind of starts growing very fast. And as you can imagine, what will happen is that this will continue to put pressure on more and more steel and iron generation as we do so much of wind deployment going forward. Composite material itself has a big carbon footprint in terms of its generation. So overall, if you look at it, the whole carbon footprint, if you look at it, of the windmills primarily comes from steel and iron. Like remember, for solar what we talk about is the crystalline silicon is a prime responsible material which is responsible for the carbon generation. In case of windmills, it is primarily the uses of steel and iron which is primarily responsible for this carbon footprint generation. And if you then start looking into the material supply chain challenges, what you will see is that many of these materials has this is increasing demand on the rare earth element. But the bigger concern, again like a similar story what was happening in solar also, many of these if you look at the wind supply chain analysis, what you will see is that again one country, specifically China, has a lot of control on the overall supply chain, be it plastic, silicon, silica glass, cement, rare earth, lead, even on this side iron and steel, aluminum. A lot of this supply chain is again controlled by one country. So effectively it is China which is kind of controlling the whole renewable energy transition of the world, because solar and wind, which are the two prime sources which are responsible or which are seen as the potential transition for this renewable energy generation, the supply chain of both the things seems to be getting kind of controlled by one specific country, and which is not a very comfortable situation for world to put so much of onus on these two technology, and it is becoming geographically limited with respect to its supply chain. So that is a concern. And the another concern is with respect to the manufacturing also, because while materials is one part of it, again on the manufacturing side, if you start looking into the key manufacturing parts includes blade, towers, necklers, generators. Again it is China which is has the maximum in terms of the manufacturing capacity also of all over the world, which is followed by North America and Europe. But again it is one country which is kind of controlling the not only the material side but also the manufacturing side of the story. So this is a cause of concern on this renewable energy sources also. And so supply chain diversification is becoming an important industry policy objective as far as the supply chain also goes into picture. If you start looking in terms of investment, what you will see is that maximum investment which is happening in wind is coming from China. As you can see, that this is a wind area both onshore and offshore, and as you can see the maximum amount of investment which is going here is coming from a specific area which is China. If you look at the whole installation which is happening, so China is the prime thing which is responsible for this onshore wind as well as for offshore wind also. Prime kind of investment is coming from China itself. The second thing which is putting money into this offshore wind is Europe, and both for onshore wind and offshore wind, but is primarily China which is kind of putting the money in this whole thing, followed by Europe, and then it is followed by North America, both for onshore wind and offshore wind. So these are prime three geographies which is putting a lot of money into this. So what we need to see that there is a bit of Asia excluding China, which is primarily India. If you look at it, India is primarily putting its onus onto onshore wind as of now. But if you look at overall investment on this sector, like if you look at offshore wind specifically, the investment is coming almost equally from China, Europe, Europe more than China also here, and North America. So these are three geographies where this investment is primarily coming into. And as far as the onshore wind goes, it is primarily China, followed by North America and some European countries, and India specifically. So, onshore wind is slightly more distributed, offshore wind is primarily 3 geographies which is driving it. But if you put it all together, it is not only the material side of the story, it is not only the manufacturing side of the story, even the investment is coming primarily from China in these two things. And this is not a surprise given that China is the highest emitter in the world. So, they are putting a lot of work around putting this renewable energy sources, but the concentration of the effort is something what is a concern of the world overall. But investment has been impressive. It is about 196 billion in 2024, less than solar. If you put it as solar was about 445 billion US dollar, both put together was about 250 billion US dollar, both put together. So, that is impressive, but overall what is the cause of concern is that China remains the largest investment market, accounting for almost half of the global investment, and that is what is slight bit of concern, but more spread should be kind of achieved around this thing. If you look at the financing structure of wind projects, it is are typically financed through project finance structure. They typically include a mix of debt and equity. As you can see that the instrument is coming more both from the debt side as well as from the equity side. The structuring is happening from both sides. It is a project level thing which is kind of driving from the European side and the North American side also. So, it is kind of project financing which is a mix of debt and equity. Long term PPAs are signed to ensure revenue stability. So, it is kind of a policy driven kind of a framework which is driving this whole investment which is coming into this sector. So, a lot of stable policy frameworks and predictable electricity market are critical for long term capital to flow in this market, and that is another thing which this sector will kind of depend upon and we look forward to. If we start looking then in India, India wind energy potential is also interesting and not as good as maybe some of the North American countries or Brazil or some of the other geographies. But having said that, overall if you start looking into India, the India key development is around this part of India is with the kind of key development is happening. So, Tamil Nadu, Andhra Pradesh, Karnataka, Gujarat, Maharashtra, Rajasthan. So, these are kind of geography which will kind of is driving the whole pathway of this renewable energy, wind energy deployment in India. The CUFs are not as impressive as the word CUF, but having said that, the CUF are typically of the order of 30%, which is higher than the solar thing. So, there is some potential on Ladakh, but there are some other ecological concerns of putting these windmills in this area. So, that is why not lot of deployment is happening in this area so far. So, most of the deployment in India has really been concentrated into this geography. So, with this, the current installation in India has been of 54 gigawatt, which is impressive given that where India kind of started. And India actually, if you look at India's journey started back in 2009, 2010, almost like when solar started. The journey has kind of ramped up from that phase. Actually, if you look at the initial years, the deployment of wind was much higher than the solar deployment, because already it was a proven technology in the domain itself in those years itself. But what we saw was in between there was a period when there was a kind of a flattish kind of a deployment of wind which was happening. But of late there has been resurgence in wind deployment. It has primarily come from a hybrid project between combining wind and solar, and I will show you why it is happening this way. But wind has kind of got a new lease of life recently in recent years, specifically with more and more hybrid projects which is coming, wind and solar. And reason for that is that the wind generation in India, if you start looking into this for a specific geography as per a research paper, but if you start looking into this renewable energy generation, what you will see is that typically the months of maximum generation, though there is a huge seasonal variation, as you can see, much higher than what you saw in solar. So, there is a huge seasonal variation. As you can imagine, there will be a seasonal variation because wind depends a lot on the weather patterns, depends a lot on what is the temperature difference between two geographies. Landlocked area will not have that kind of a high wind speed, so that will always be a cause of concern. But overall, if you look at it, that there is a huge seasonal variety around it, but the seasons in which it is generating more are the season in which solar generates less. So, when it generates more is during the rainy season. So, maximum generation months are, what are the maximum generation months? August and September. And August and September, since there is a huge potential of rain happening, So solar generation is usually not so good in those specific months. So it kind of complements very well to the solar generation. And if you look at the hours of generation also, usually solar energy generation usually takes place during the daytime, but wind is kind of available throughout the day. But if you look at overall trend of wind generation, it has a kind of a dip in the day. Like I'm not talking about those two specific months, but if you look overall, wind generation is higher in the morning and the evening, which kind of complements the solar generation a lot. So this brings a very interesting perspective that if you can then combine the plants of solar and wind together, then you can have a potential of generating the energy almost throughout the day in some form or the other, with some source or the other. And with this in mind, what is happening is that a lot of studies has been done in solar wind complementarity, and what is seen is that solar and wind can complement each other a lot, because solar kind of peaks during the daytime, its highest output is during the summer months. Wind power often is stronger during the evening and night hours, and its higher output during the monsoon and winter season. So overall there is a huge complementarity which is seen between these two technologies. And with this in mind, India is putting a lot of emphasis on a hybrid projects, which is a combination of wind and solar both put together. And with this coming into picture, what is seen is that look at the combined CUF for this specific geography, like for Hyderabad for example. Look at the combined CUF. We are talking about a CUF of about 0.53. In Mumbai, we are talking about a combined CUF of 70%. We are in Trivandrum, it is more 40%. So overall, if you start looking into that we are looking at specific geographies where these hybrid plants can give very high CUF. And if you start talking about CUF that kind of an order, the renewable energy can start looking more and more impressive if you start putting both the things together. And with this in mind, what is happening is that more solar and wind hybrid projects are being put in tender these days. Advantage include higher combined utilization factor, better utilization of transmission infrastructure, because transmission not only supporting solar in the daytime or not only supporting wind when wind is available, but putting together the transmission system can be more utilized and more flow of electrons can happen on that almost throughout the day. There is a reduced intermittency in the power output, which is another interesting factor. So overall economic viability of renewable projects kind of goes up, and that's why India has introduced policy to promote large scale wind solar hybrid through this introduction of national wind solar hybrid projects. This is a new policy which has come up in recent years, and that is looking very interesting. And so though as of now when we speak, the hybrid capacity is about 7.7 gigawatt, which is not as significant compared to 125 gigawatt of total installation, but the projects which are in pipeline are pretty impressive, about 30 gigawatts. So this is the trend in which it will kind of move. So the overall wind, while it has its own potential of generation, while it has its own potential of huge energy generation, specifically in geographies which are around the coastal areas, specifically in the geographies where the temperature difference between the land and the sea, or between the mountain and the land area, so around the snowy peaks and land around it, so wherever the temperature difference is. So while that energy generation potential is high in those geographies, but even for the geographies where, for like India, where you don't have so much of snow-clad mountains apart from the Himalayas, if you come down from there, there is some coastal area availability which is there. But overall, if you start, given the high potential of solar in India and given the potential of wind in India, if you start putting it together, this whole thing can start looking very impressive and very interesting. And that is what the Indian policy makers are now heading towards. And more projects are being now pushed, which is a hybrid of solar and wind, and that is what it has given a new lease of life to wind, and which I was talking about, that after a period where the wind deployment was becoming almost flattish, it has again seen a new lease of life, and more projects are being pushed through in this domain. And with this, almost the future technology which I already talked to you about, that the larger rotor diameters are coming, higher hub heights are coming, blade materials are coming. These will continue to improve the per square meter of deployment. So in terms of the footprint area, since the swap area will go up, and since the motor speed, the rotor type, the generator efficiency, everything will kind of keeps on improving a lot. So generation of future wind projects looks very impressive, and if you start then putting it together, it could be a very interesting thing along with the solar, with the combined technology. Of course, there are few challenges which I kind of mentioned in between also, that there is a variability of wind resource which we have to take care of it, and it could lead to some issues on the grid stability. It could also lead to some issues with respect to CUF not being stable, unlike solar CUF is much more stable. Wind CUF is not as stable as the solar CUF is. There could be land use constraints also, because potentially it could lead to a situation where the wind is moving. So, there has been some reports in Europe at few places where some residents have kind of put concerns that it kind of disturbs the ecology of their specific geography, because there have been, this has impacted the movement of birds in that area. It has impacted the what kind of noise these windmills are generating during their operations, as there is a rotation part around it. So those kind of concerns keeps on coming, and that's why the offshore winds are becoming slightly more popular as we kind of go along. There are transmission infrastructure limitations. We already talked about it, because intermittency of the whole source. And last but not the least, there could be supply chain bottlenecks for turbine components, because specific material uses, concentration of the ownership of those materials by specific countries, and also the manufacturing also is limited to specific countries, which is a slight concern if you really want to put your lot of bet on this technology overall. But having said it, what we are seeing is that wind and solar together are expected to become the backbone of future power system. And given the complementarity of the two technologies, given that they can kind of support each other in a very, very interesting way. So with that in mind, these two combined can become a dominant sources of electricity in many, many decarbonized power systems. Together they offer abundant renewable energy sources, declining generation costs, complementary generation patterns. So overall, this is putting together, and now you can go back and now can start making sense of it, that when the world is putting an energy transition plan, it is putting a lot of onus on electricity, and under that electricity onus, it is putting a lot of onus on wind and solar. And now you can understand why so much of onus is being put on this together. And of course, the next thing that we will start looking into from the next lecture onward is that still there is an intermittency issue, that it is still not 100% CUF which we are talking about. Still there is an issue where we are talking about that the generation could be unstable, and for that what we have already, some of you would recall I talked about, is that we will need storage as a complementary technology to this whole transition. So from next lecture onwards, we will start looking into that, what does the storage technology is, where does it stand, what is coming in the market, and how it is kind of supporting this whole journey of this solar and wind dependent energy transition movement, which is electricity dependent movement. How what role and what form the storage would look and kind of support into this energy transition movement. Thank you, and see you in the next class.